let's talk about work and energy. Work is very similar to torque, with the exception that work is force that is parallel to a distance. Now, I like to have a little bit of fun with it. I know that force is equal to mass times acceleration, and then distance is still the same. So I like to tell my students that work makes me mad. This is an easy way to remember the formula, and it helps out when you have different variables. So work makes me mad. And then work is also measured in joules. So work is really the force applied parallel to a distance. Okay, and then we need it, and it's measured in joules. Now let's talk about energy. We have two main types of energy that we talk about in this unit. And so we have potential energy. And potential energy is depicted by the capital letter U. It is also measured in joules. And potential energy is the potential to do work. You can also say that it is stored energy, which is usually what your students are going to say, or what you've learned in the past. It's stored energy. Anytime you're sitting on your couch or you're moving around, those are two different types of energy. So when you're sitting on the couch, that's stored energy. When you get up to go to the dishwasher to put your plate away or get some food, that's kinetic energy. So kinetic energy is depicted by the capital letters KE, and it's also measured in joules. And this is the energy of motion. So now to the formulas. We know that work makes us mad. Potential energy is mass times gravity times height. And the height is really important because the height is what determines your potential energy. The higher up an object is, the more potential energy that it has. The lower it is, the less it has. And you can think of roller coasters with this. Those are a great example. You don't want to go on a really short roller coaster. It's very lame. It doesn't go very fast. It doesn't have a whole lot of energy. And the reason is because it doesn't start out very high. When we look at this, we know that mass is going to stay the same, and gravity is just an acceleration due to gravity, and height is really a distance. So potential energy also makes me mad. When we look at kinetic energy, however, it's a little bit different. So kinetic energy is equal to 1/2 mass times velocity squared. When we talked about centripetal motion, we realized that velocity squared is really the same as meters squared per second squared. So we have meters squared per second squared. We can take a meter out of this. When we take a meter out of this, this becomes distance, because we have to take a meter out, multiplied by meters per second squared, which is an acceleration. So here we have our add for our mad, and we still have our m, and this is measured in kilograms. It's just easier to show you with the meters squared per second squared, so you can relate that to acceleration. So kilograms, and our kilograms is still a mass, but it's multiplied by 1/2. So I tell my kids that force or work makes me mad, potential energy makes me mad, kinetic energy makes me half as mad. And these are all interchangeable. These are all interchangeable because of what we call the law of conservation of energy, or LOCE, as the short term is much easier to write. So law of conservation of energy means that the total amount of energy, E total, is equal to kinetic energy plus potential energy. This does not mean that total potential energy plus total kinetic energy is equal to total energy. That is not true. And I'm going to explain that by using a roller coaster diagram. Yay, roller coaster. Here's our card at the very, very top, and it has total potential energy. So when you're on a roller coaster, you start about halfway up, and then you click, click, click all the way up to the top of the roller coaster. And then at the top of the roller coaster, you pause for just a second where you have total potential energy. So up at the top, we have total potential energy. And then as we begin to slowly come down, we go faster and faster and faster. And as we get to the very bottom, we're going the fastest that we possibly can go. And this is where we have our total kinetic energy. Now, halfway through, obviously, we don't have our total kinetic energy because we don't have the greatest amount of velocity, which is what determines our kinetic energy. And we don't have the total amount of potential energy because we don't have that total height that we started with. And so here we have 1/2 of our potential energy plus 1/2 of our kinetic energy. So this is where the law of conservation actually shows itself the best. Here we have 0 kinetic energy, and here we have 0 potential energy. Looks like OU, but that's not the way it's supposed to be. So 0 kinetic energy, 0 potential energy down here. So total energy here would be the total energy, and total kinetic energy here would be the total energy. Now this happens all the way through. So here, if we have 1/4 kinetic energy, roughly, and here we have 3/4 potential energy, roughly. So this works all the way around, and your velocity is dependent on that kinetic energy at different places. So remember that total kinetic energy plus total potential energy is equal to total energy, and you can also throw work in there because it is dependent upon the amount of total energy you have.